Welcome back. I filled up my phone because I forgot to delete old videos and I'm that kind of smart. But let's get back into the combined gas law. Remember what it says, the initial pressure times the initial volume all divided by the initial temperature equals mathematically the after pressure times the after volume all divided by the after temperature, no matter what the change is. So it doesn't matter what kind of mucking around you do, the before mathematically equals the after when done this way. So let's walk through this. Now I'm about to do algebra. No, why? Why would you do that to us? So if you hate algebra, if you hate math, if you're getting scared just by hearing it, just kind of sing songs in your head. I'm going to give you a phrase and probably write it right up there. I'm going to give you a phrase that takes all the math out of it. But I'd like to show you the math before I take the math out. So let's say that what I'm going to do, let's say that the change I'm going to make is I'm going to double the pressure. So we're going to say that the new pressure is actually twice the old pressure. So whatever the new pressure is, I double it. Now, how are the volume and temperature going to handle? What's going to happen with the volume and temperature? Now, I'm going to make another assumption, and the other assumption I'm going to make is that the volume's not going to change. I'm going to assume that it's like a canister, like a scuba diving tank, and as the pressure changes, the volume, the size of that tank stays the same. So I'm just going to assume for this problem that V2 equals V1. So now the question is, what's T2? How's that going to, how do you even predict that? And the answer is, well, this is mathematically even. So we can actually do math and put numbers in and figure this out, but we don't even have to put numbers in. We can stay in the world of variables because I notice a couple things. First thing I notice is there's a V1 on both sides. Look at that. Oh my gosh, it's amazing. I notice that there's also a P1 on both sides. And so now we get to the point of, well, we can cross multiply, and actually the math isn't really terrible for this. Let's see. If we cross multiply, we get this 2, which hasn't been crossed out, times this T1, and that has to mathematically equal, well, everything's been crossed out there, so that's going to just be the number 1 times T2. And since T2 times 1 is just T2, we get, oh my gosh, what's going to happen in temperature? It's going to double also. Twice the original temperature is going to be this final temperature. So if I double the pressure, I double the temperature. Oh, hey, didn't we talk about that? How like they're directly proportional. If I double one, the other one doubles. Oh, look, mathematically it works out. Hey, he wasn't lying. Isn't that amazing? Okay, that's the math, and you can do a cajillion problems like this. Just cross multiply, and you solve for the thing you don't know and get it by itself, and the number tells you the answer. But for people who don't like math, that's everybody. That is not true. I absolutely love math. In fact, that's my major. Why would you major in such a terrible thing? Because I love it. And I was under the impression also if I majored in math, I'd be able to make a lot of money after college. Then I became a teacher. Moving on. So here's the combined gas law. P1, V1 over T1, P2, V2 over T2. They're mathematically equal. Here is the phrase that I like to tell students to help them kind of navigate how to do this without math. And here it is. If they are on the blank level, they act blank. And if they are on blank levels, they act the blank, period. Now, if that doesn't make sense, nothing will. Wait, what? And here's the thing that's missing. If they are on the same level, they act differently. And if they are on different levels, they act the same. Now, what the heck does that mean? To truly understand this, we're going to have to rewrite this a little bit so that we can start using colors to help identify. But I'm colorblind. I am too. It's really kind of a bummer, but that's how it is. Okay, we'll do orange will be our pressure. Green will be our volume. And blue will be our temperature. Okay, so if they are on the same level, they act differently. Well, when I look at this formula right here, or this one over here, I notice that P and V are on the same level. They're both on the top. And what that means is that they act differently. So if they're on the same level, such as the P and the V, then what we would get is we would get them to act differently. They would be inversely proportional. As the pressure increases, the volume is going to decrease. And we remember this from if I take a balloon out into space and lower the pressure, the size of the balloon increases. Or vice versa, if I take the balloon and I take it underwater and increase that pressure, the balloon gets smaller. So because these are on the same level, they act differently. So as pressure decreases, volume increases, and vice versa. So if they're on the same level, they act differently. What if they're on different levels? Well, let's look at those, such as the pressure and the temperature. Those are on different levels. Well, if I increase the pressure, as in I have them move, push harder, that means they're moving faster. Oh, they act the same. And if I decrease the temperature, they're going to push less. Oh, that's right. Because P and T are on different levels, they act the same. As the pressure or temperature changes, the other changes in lockstep with it. And the final one is V and T. Well, these are on different levels. This is on the top, this is on the bottom. So we'd have, if it's on different levels, it acts the same again. Again, if I increase the volume, if I increase the temperature, the balloon's going to get bigger. If I decrease the temperature, the balloon's going to get smaller, right? So these, again, are in lockstep because they are on different levels. So if they're on different levels, one's on the top, one's on the bottom, they're going to act the same. If they're on the same level, then they act differently. So that phrase right there, I would definitely put in my notes. In fact, I'd pause the video right now and write that down. If they're on the same level, they act differently. If they're on different levels, they act the same. Pause and then come back. Welcome back. And way to follow what I said. Okay, so how are all these things related? Well, let's find out. Just for reference, down at the bottom, I'm going to write my combined gas law formula. I'm just going to write the front of it because that's really all I need. And let's just start in. Okay, so we have pressure and volume, right? So pressure and volume are, well, let's see, they're on the same level, so they act differently, which means they are inversely proportional. Pressure and temperature, let's see, pressure and temperature, they're on different levels. One's on the top, one's on the bottom. So different levels act the same, are proportional. And last but not least, volume and temperature. Volume and temperature, oh, that's a V. They're on different levels. One's on the top, one's on the bottom. If they're on different levels, they act the same, are proportional also. And since I'm a visual learner, what that means is volume and temperature are proportional. Volume goes up, temperature goes up. That's what proportional means. Pressure and temperature are proportional. If pressure goes up, temperature goes up. And pressure and volume are inversely proportional. If pressure goes up, volume goes down. There you have it. That is the combined gas law, which combines Gay-Lussac's law, Charles's law, and Boyle's law all in one cute little formula. And you can use it to predict how gases will act after changing something. So there it is. Good luck.